Welcome to the numerical problem segments. Here we will discuss a couple of numerical problems attributed to the proximate and ultimate analysis and heating value. As you know that we have discussed these theoretical part in the previous lectures. So, first thing we will discuss about the numerical problems pertaining to the power cycle, and second aspect we will discuss about the numerical problem pertaining to the proximate and ultimate analysis. Now, let us have a look about the first problem. Now, this first problem says that dry and saturated steam at pressure 11 bar is supplied to a turbine and expanded isentropically to a pressure of 0.07 bar. Now, you need to calculate the heat rejected, heat supplied and theoretical thermal efficiency. Now, for the ease of the business, because sometimes you may require the value which are available in the steam table, we have given the values, whatever values required for the calculation of this particular problem. Now, you need to determine the heat rejected. So, that is the determination of heat rejected, that is given by QR is equal to H2 minus H3. Now, remember we have already supplied this PV as well as the TS diagram for the convenience. Now, how we can find out the unknown H2? Now, before we go for finding out the unknown H2, let us have a look about the what we are looking for. So, for first isentropic expansion occurs. So, therefore, S2 is equal to Z1, that is 6.554. Now, since for wet steam at point 2, S2 is equal to plus X, that is the dryness fraction, and SFG P is equal to 0.07 bar. We have taken this value from steam table. Therefore, C plus X2 SFG, that is fluid to gaseous form, at P is equal to 0.07 bar is equal to 6.554. Now, it is 0.559 plus X2 7.718, that is equal to 6.550. So, by this way the X2, that is the dryness fraction, comes out to be X2 is equal to 0.776. So, enthalpy for wet steam, at point 2, that is H2 is equal to HF plus X2 HFG, fluid to gaseous form, at P is equal to 0.07 bar. Now, H2 is equal to 163.4 plus 0.772 into 2409, this value is given during the problem, and that is equal to 2032.9 kilojoule per kilogram. So, by this way we can calculate the heat rejected, that is QR is equal to H2 minus HF, that is equal to 2032.9 minus 163, that is comes out to be 1869.9 kilojoule per kilogram, and that is the answer. So, that is the heat rejected, that is QR is equal to 1869.9 kilojoule per kilogram. Now, come to the next part of the problem, that is the determination of determination of heat supplied, that is QA. Now for this we need to seek the help of a mathematical relationship, that is work done during cycle W is equal to heat supplied QA minus heat rejected QR, or some other words, QA is equal to W plus QR. Now for finding unknown W, network done during cycle W is equal to total work minus WP. So again we need to find out the unknown WT and WP. So turbine work WT is equal to Hg1 minus H2 is equal to 2779.7 minus 2032.9, and that is 746.8 kilojoule per kilogram. Similarly, if we talk about the pump work, WP is equal to VF P1 minus P2 10 to the power 2, and that is 0.001 11 minus 0.07 10 to the power 2, and that is 1.093 kilojoule per kilogram. So W is equal to turbine work minus pump work, and that is 746.8 minus 1.093, and that is 745.7 kilojoule per kilogram. So QA is equal to W plus QR, and that is 745.7 plus 1869.9, and that comes out to be 2615.6 kilojoule per kilogram. This is the desired result. Now at last, that is the third point, we are looking for determination of theoretical thermal efficiency. Now this can be calculated by work done during cycle divided by heat supplied multiplied by 100. So we have already calculated the required values, that is 745.7 divided by 2615.6 into 100, and that is efficiency is 28.5%. So this is the desired result we have calculated by this way. Now let us move to the another problem. Now this problem suggests that a steam turbine receives steam at a pressure of 20 bar and superheated to 88.6 degrees Celsius. The exhaust pressure is 0.07 bar and the expansion of steam takes place isentropically. So we need to calculate the heat rejected, heat supplied. For this we need to take an assumption that the feed pump supplies the water to the boiler at 20 bar, and we need to calculate net work done by the turbine, thermal efficiency and theoretical steam consumption. Now here the superheated steam supplied to the turbine at pressure P1 is equal to 20 bar. Now the temperature of superheated steam is equal to T plus 88.6 degrees Celsius. Now for this we need to seek the help of steam table, that is the dry saturated steam. So at pressure P1 is equal to 20 bar is equal to 212.4 degrees Celsius. So therefore the temperature of superheated steam 212.4 plus 88.6, and that is 300 degree Celsius. Now again for superheated steam, at pressure P1 is equal to 20 bar, and we have find out the temperature T 300 degrees Celsius. So enthalpy is equal to 3025 kilojoule per kilogram, and entropy is 6.768 kilojoule per kilogram. Now we have already given that steam expanded isentropically to pressure P2 0.07 bar. So again we need to seek the help of steam table for the dry saturated steam. So at pressure P2 0.07 bar, this is the enthalpy, that is 163 kilojoule per kilogram. HFG, fluid to gas, 2409.2 kilojoule per kilogram. Entropy 0.552 kilojoule per kilogram Kelvin. SFG, this is equal to 7.722 kilojoule per kilogram Kelvin, and V volume, specific volume, is equal to 0.001 meter cube per kilogram. Now for dry saturated steam, at pressure P2 0.07 bar, HF is 163 kilojoule per kilogram. HFG 2409.2 kilojoule per kilogram. SF 0.552 kilojoule per kilogram Kelvin. SFG is equal to 7.722 kilojoule per kilogram Kelvin. V3 is equal to, or specific volume, 0.001 meter cube per kilogram. Now we are having the data with us. So determination of heat rejected, QR is equal to H2 minus H3. So we need to find out the H2. So isentropically, expansion, so therefore S2 is equal to S1, and that is 6.768. Now for wet steam, S2 at point 2, S2 is equal to S3 plus dryness fraction, and SFG at P is equal to 0.07 bar. Therefore, S3 is plus X2, SFG 0.7 bar is equal to 6.768, and 0.552 plus X2 7.722, and that is 6.768. We calculated X2 is equal to 0.8047. So enthalpy for wet steam at point 2, H2 is equal to HF plus X2 HFG, P is equal to 0.07 bar. Now by this way we can calculate H2 is equal to 163.4 plus 0.8047 multiplied by 2409, which we have previously calculated, and that comes out to be 2101.52 kilojoule per kilogram. So heat rejected QR is equal to H2 minus H3, and that is 2101.52 minus 163, and that is 1938.52 kilojoule per kilogram. Now another thing, that is determination of work done by turbine. Done by turbine, WT. So turbine work, WT is equal to superheated enthalpy at point number 1 minus enthalpy at point number 2. So this turbine work WT is equal to 3025 minus 2101.52. This comes out to be 923.48 kilojoule per kilogram. The next step is that determination of net work done. Of net work done, that is W. So the net work done during the cycle can be given as W is equal to turbine work minus pump work. Now since we don't have any clue about the WP, that is the pump work, so pump work WP is equal to specific volume at point number 3, P1 minus P2 10 to the power 2, that is 0.001, 20 minus 0.07 to the power 2, and that is 1.993 kilojoule per kilogram. So net work done during cycle, WT minus WP, and that is 923.48 minus 1.993, and that is 921.487 kilojoule per kilogram. Now next, determination of heat supplied. That is sometimes referred as QA. So it is given as net work done during cycle is equal to heat supplied QA minus heat rejected QR, or QA is equal to W plus QR. W we have already determined. So QA is equal to W plus QR, and that is 921.487 plus 1938.52. This is 2860.0 kilojoule per kilogram. Now let us talk about the thermal efficiency. Now this is equal to net work done during cycle divided by heat supplied multiplied by 100. So we have already calculated the relevant information, that is 921.487 divided by 2860 into 100. It comes out to be 32.21%. This is the thermal efficiency of the system. Now at last we can calculate the theoretical steam consumption. This is given by 3600 divided by net work done. 3600 divided by 921, which we have already calculated. This is given as 3.91 kilogram watt hour. So this is the desired result. Now let us take another problem that is related to the Dimas method. So 0.1688 gram when analyzed by the Dimas method yields 31.7 ml of moist nitrogen measured at 14 degrees Celsius and 758 mm of mercury. Now you need to determine the percentage of nitrogen in the substance. It is given that the aqueous tension at 14 degrees Celsius equal to 12 millimeter. Now weight of, let us solve this problem. It is weight of organic compound, that is 0.168 gram, volume of moist nitrogen V1 is equal to 31.7 ml or 31.7 into 10 to the power minus 3 liter. The temperature given is T1 14 degrees Celsius or 287 Kelvin. Now pressure of moist nitrogen P, that is 758 mm of mercury. It disappeared here. Cut it. Right. The pressure of moist nitrogen is 758 mm. Now aqueous tension at 14 degrees Celsius is 12 mm of mercury. This is given in the problem. So the pressure of dry nitrogen, that is P minus P1, which is equal to 758 minus 12, 12 which this is given here, and that is 746 millimeter of mercury. Now let us take our Biot formula. P1 V1 upon T1 is equal to P naught V naught upon T naught. So need to calculate the V naught. So 746 into 31.7 into 10 to the power minus 3 divided by 287 into 273 upon 760. So V naught is equal to 29.58 into 10 to the power minus 3 liter. So percentage of nitrogen comes out to be 28 divided by 22.4 into V naught upon W into 100, and that is 28 upon 22.4 liter. 29.58 divided by 0.1688 into 100, and that comes out to be 21.90%. So this is our desired result. Let us take another problem. In this problem, that is a problem number 4, the 0.2 gram of an organic compound was analyzed by Zeldal's method. Ammonia evolved was absorbed in 60 ml N by 5 H2SO4, and unused acid, this required 40 ml of N by 10 NaOH for complete neutralization. Now your objective is to find out the percentage of nitrogen. Now here the 60 ml N by 5 H2SO4, that is 12 ml if we convert this to H2SO4, and 40 ml N by 10 NaOH equivalent to 4 ml NaOH. Now acid used with ammonia, that is 12 minus 4 or 8 ml normal H2SO4. So therefore the percentage of nitrogen is equal to 1.4 into normality of acid into volume of acid used with NH3 divided by weight of organic compound. Now we can consider normality of acid 1N. So the percentage of nitrogen is equal to 1.4 into N into V upon W, and that is 1.4 into 1 into 8 divided by 0.2, and that comes out to be the 56%, and that is the answer. So in this particular segment we have carried out some sample example of the theory which we have carried out in the previous chapters, and I hope that all of you have gone through this, the concept of ultimate and proximate analysis as well as the other concepts. By this way, thank you very much for paying attention.